So welcome to this latest video on 162 Maths, and in this video we're going over the AS Maths Mechanics topic of Kinematics, introducing SUVAT. Now when we are given a velocity time graph, where there are two key properties that we need to be aware of. Now one of them is that the gradient is equal to the acceleration. So just a little reminder on how we find that to find the gradient, all we need to do with the line is find our right angle triangle, find the distance across and the distance up, making sure that we're using the correct units on the axes stated, and that the gradient is going to equal the distance or the height of that triangle over the base of that triangle. And obviously a positive line will therefore represent acceleration, a negative gradient would represent deacceleration. Now from this we also know that the area under the curve equals the displacement. So if I'm wanting to know the area travelled after, let's say, t minutes, then all I would need to do is, let's just represent that with a different colour, is find the required t value from 0 or from another initial time period and work out the area under that line, and that would equal the displacement. Now from that, what we also then know is that in this particular section, your line on the velocity time graph will always be a linear line, which therefore means that acceleration will always be constant. Now you can get graphs on the velocity time graph where it's represented by a curve, but that's going to be sort of revisited in year 13, so it's more of an A2 topic when acceleration is not constant. Now calculating the gradient or the acceleration in a general sense, what we need to do is, now as you can see with the yellow line, we've got our constant acceleration. Now this point here is going to be represented by when t equals 0, and this point here is what we're just going to call u, is our initial velocity. And after t seconds, which I'll just label this here, and that is there, we can see that the velocity, the final velocity, which we'll call v, is at that point there. Now to find the acceleration of this, we need to find the gradient of that yellow line between these two values. Now the height of that triangle is v minus u, and the base of that triangle is going to be t minus 0. So to work out the acceleration using the gradient formula, it's going to be v minus u over t, in which we can rearrange this to make v the subject as at equals v minus u, and so v equals u plus at, and let's just put a little box around that formula there. Now to calculate the area under the line, or our displacement, what we'll have after t seconds is we need to work out the area under the curve after t seconds. Now this will either be in the shape of a trapezium or the shape of a triangle. Now it doesn't really matter which one we use, whether it's a triangle or a trapezium, because when it's a triangle, the distance of one of our parallel sides will equal 0. So the same thing applies in terms of the formula. And the formula for a trapezium is actually derived from the area of a triangle. So if we wanted to work out what this area here is using this notation, just to recognize that S is our displacement, then to work out the area of trapezium, we add our two parallel sides, which is this side here is going to be u, this side here is going to be v. So to work out S, it's going to be u plus v multiplied by the height of that trapezium, which in this case is going to be t, and we divide that by 2. And another way of writing this is that S equals a half of u plus v t, or we can write it as S equals a half t u plus v. And what we then establish is that we've now derived two important formulas of motion. Now, using the formulas generated, we can also do some algebraic substitution very similar to that we did in simultaneous equations to make different formulas using different variables. So if I start by calling our displacement formula 1 and our velocity formula 2, or final velocity formula I should say, then if I substitute 2 into 1, what I end up with is s equals a half u. Now instead of writing v, I'm going to write this instead, so which I've got u plus at, and that's with the t there. Now if I multiply and simplify, I get s equals a half 2u plus at multiplied by t, then multiply the half out, in which I get u plus a half at all multiplied by t. I get an S formula of ut plus a half at squared, and that is going to be my third formula. Now similarly, what we can do is we can rearrange this to make u the subject, so u is going to equal v minus at, and so if I now substitute this, which I'll call, I don't want to get confused in terms of what I'm calling the formula, so if I sub this into equation 1, then what I end up with is s equals a half. Now instead of writing u, I'm going to write v minus at, and that's plus v and multiplied by t. So again, simplifying, I get s equals a half, it's going to be 2v minus at times t. S equals, multiply out the half, I get 1v rather. So I'm going to get v minus a t, and let's stick a half there. So a half a t all multiplied by t, giving me another formula of vt minus a half a t squared, and let's just put a little box around that and call that equation 4. Now lastly, if I take that formula 2 again, so our velocity formula, and I do a bit of rearranging, this time let's make t the subject. So if I make t the subject, I'm going to get v minus u all over a, and let's call this one number 5. So again, if I substitute 5 into my equation 1, then what I'm going to end up with is s equals a half u plus v, and instead of writing t, instead I'm going to write this instead. So what I've got is I've got v minus u over a. Now obviously, to neaten this up, this looks a bit of a mess. Let me just neaten up that little bracket there, and what I end up with is remembering that this is equal to a half multiplied by u plus v multiplied by v minus u over a. Now as you can see, I've got a mixture of sort of constants, and I've got fractions as well. So if I turn that integer into, let's say, a fraction, well, I don't know if it's going to be an integer, but again, we haven't got a non-fraction, I should say. Just write that over 1. Then to multiply fractions, all I do is multiply the numerators together and multiply the denominators together. So here what I've got is I've got s equals 1 times uv multiplied by v minus u over 2a. Now with this one here, if I just switch that around, the two variables, then what I get is v plus u, v minus u over 2a. Now one thing that you should be able to notice about these two things here is that it's a difference of 2 squares. So from this, I can then simplify this as v squared minus u squared over 2a, equals s. And what I can then do from there is I can rearrange this to make v squared the subject. Why, you may be asking? Because I can, and also that v squared is my first variable here, and I'm subtracting u squared. I don't really want to make u squared because I'll have to then change the sign, so v squared here is going to equal 2as plus u squared, and if I just rearrange this, then what we get is u squared plus 2as, and this is my fifth formula for me to remember. Now note, when using the formula of velocity squared equals u squared plus 2as, notice that calculating v, that v could be positive or negative when you square root. But what does this mean? Well, as you can see from the graph, at point A the velocity will have the same value but on the opposite signs as the particle is moving in the opposite direction. Now before we get started working through some worked examples, now these 5 formulas can be used to solve problems in situations where the assumption that acceleration is constant. So before attempting these questions, always make sure that you're looking out for words of that the acceleration is either uniform, constant, steady, even or continuous. It's one of those things where you'd need to check for. It's sometimes automatically implied, particularly at AS level, but it's a bit like solving a quadratic, making sure that it's equal to 0. Most questions will have it equal to 0, but some questions might deviate, in which if you do get a question where it doesn't mention that, then it's more likely to appear on an AS2 paper or an A-level paper. So please be mindful of these questions when you are doing your revision or practicing SUVAT. Now, in terms of in practice, some of these formulas are used more frequently than others. So as you can see, a lot of the formulas that we're given for SUVAT, S is the subject. So you may need to rearrange those formulas, but in terms of how they're usually represented in the formula book, this is how they are represented, as you can see in the green box. Now, although these formulas may look complicated, particularly when you're seeing them for the first time, rest assured that these formulas are given to you in the formula book. But it's one of those things where if you're persistently practicing SUVAT, you will learn to know these formulas off by heart. So don't feel anxious about having to remember these formulas, as they are given to you in the exam. Now before we get started working through some examples, just a few tips and guidance. So what helps answer questions related to this topic is structure, understanding what is being asked and the information given. So when solving problems, be systematic. Identify and list the variables with known values and the variable that you're trying to evaluate. This will help you decide which formula to use. And what I mean by that is, if you think back to SOHCAHTOA trig or right angle trig, you've got 3 different ratios. You look at the triangle, you label the triangle in terms of the sides and the angles that you're given and what you're trying to find, and from that you can then decide which ratio to use. And the laws of motion formulas are done in a very similar way. So let's have a look at our first worked example. So this question says that a car travelling at 15 meters per second suddenly accelerates to 3 meters per second squared. What is its speed after 5 seconds? And now what's really important is you have the formulas in front of you so you know what to use. Now a good starting point with any of these questions is to write SUVAT. Now once you've written those 5 letters, you then want to go back to the question and start picking out what values you've been given and what it is you're actually trying to find. Now one of the common questions I always get asked as a teacher is, how do you know which one's the initial velocity and which one's the acceleration? Now a good tip for that is to look at the units. Now whenever you're looking at velocity, and that's either going to be u or v, then the units for that is going to be a distant unit, so either meters or kilometers, over time. Now when it comes to acceleration, which is our a variable, then that's going to be distance over time squared. So it's going to be the time squared units. So going back to the question, I know that a car travelling at 15 meters per second, which is my u value, so that's 15 meters per second, and we've got our acceleration value, which is 3 meters per second squared. T is 5 seconds, and what we're trying to find is we're trying to find our final velocity, which I'm just going to call X, or you can put a little question mark, whichever floats your boat with this. Now, what is important is that you look at the units. Now you want to make sure, just a quick glance, to make sure that the units are the same. So your distance units are the same and your time units are the same. Now if you do find a question where they are different, you will need to convert them so that they are. So a little bit of unit conversions may also be involved in this question. Now once you've established your 4 variables where one is missing, you then need to make sure that you're choosing the right formula. So what we're looking for is we're looking for a formula that uses U, V, A and T. So I can kind of dismiss anything that's got an S. Now for this, the formula I'm going to use is going to be the very top one. So once you've established what formula you're going to use, I always recommend students to always write down what formula it is, and then all we then need to do is substitute the numbers in. Now again, one thing that I forgot to mention is when you are writing the units in your SUVAT, just make sure that you're not losing the aspect of the number. Make sure your 5 seconds don't look like 55x, or if you're just using S, just make sure that it doesn't look like a 5, because in exam conditions sometimes you can oversee that, and it's where a lot of students also make silly errors. So going back to this question, all I need to do is substitute the numbers in. So I've got x equals 15 plus 3 times 5. So I get a V value of 30. And then all I then need to do is just write down the units, which in this case is going to be meters per second. So you can either write it as ms to the power of -1 or m/s will be absolutely fine for that one. Now moving on to our second example, it says that a car travelling at 10 meters per second accelerates to 4 meters per second squared, and its speed has increased to 18 meters per second. How far does it travel while accelerating? So again, with this, we write down our SUVAT values, and looking at the information from the question, we've got our initial speed, which is at 10, our final speed, which is at 18, our acceleration value, which is at 4, and what we're trying to find is how far it travels. So we're trying to find out what S is. So T is not needed in this particular question. Now again, just double check to make sure that the units are the same, in which they are, so I don't need to do any unit conversions. And then from this, what I then need to decide is which of the 5 formulas you can see in the green box am I going to use as S, U, V and A. Now for this one, what I'm going to be using is I'm going to be using this third one here. So writing it down, I've got V squared equals U squared plus 2AS. Now as you can see in this particular formula, I haven't got S the subject, so you could do one or two things. You can either rearrange this formula to make S the subject, or you can substitute the numbers in and solve for S, and it really doesn't really matter which one you go for, but I would say try and perfect one rather than doing both, because what you don't want to do is get yourself confused. So here, if I substitute the numbers in, I've got 18 squared equals 10 squared plus 2 times 4S. And remember, make sure that you're not getting confused with S and 5s. So typing this all into my calculator, what am I going to get? Well, I'm going to get 324 equals 100 plus 8S. And then rearranging this, so I've got 324 minus 100 all divided by 8 equals S. And it gives me a displacement value of 28. And that's going to be in meters. So here the distance travelled during the acceleration is going to be 28 meters. Now let's have a look at our third example. So it says a car moves with constant acceleration. When t equals 0, it passes a junction when its velocity is 8.2 meters per second. It passes the next junction 320 meters away 24 seconds later. Find the car's velocity as it passes the second junction. Now, what's really key about this particular question is that it starts with saying that it's got constant acceleration. So we know it's going to be a SUVAT question. So if we start by writing down our SUVAT values, and let's see what we've got. So looking at the information that's given to us in the question, we know that when t equals 0, that it passes a junction at 8.2 meters per second. So this 8.2 meters is our initial velocity. So I can write 8.2 there. It then says that it passes the next junction 320 meters away. So our displacement is 320, and that was after 24 seconds. And what the question is asking us to find the car's velocity as it passes the second junction. So what we don't know is what v is. So the one variable that we don't need is the acceleration. So what I'm looking for is I'm looking for which SUVAT equation uses S, U, V and T. And that is going to be our second equation here. So if I start by writing that down, and what I'm trying to find is V. So if I substitute those values in, I get 320 equals a half 8.2 plus V multiplied by 24. And then all I need to then do is solve this for V. Now a half times 24 is 12, so it's going to be 320 equals 12 lots of 8.2 plus V. Take the 12 over, and I end up with 8.2 plus V, giving me a V value of 320 divided by 12 plus 8.2. Now if I stick that all into my calculator, making sure that I've entered it correctly, actually that should be a minus, not a plus. So let me just get rid of that. And typing that into my calculator, I get an answer of 18.5, and all that's left for me to then do is just write down the units, and there is my answer for that one. Now example 4 says a car deaccelerates uniformly from 26.3 meters per second to 16.2 meters per second, covering a distance of 240 meters. And the question is asking us to find the deacceleration. So for this, let's first of all recall the formulas, and let's just write down our SUVAT values. So we've got SUVAT. Now from the information of the question, we have our, well, we know that it's got a uniform acceleration, so that's fine for SUVAT. The initial rate is 26.3, so that's 26.3. We've got our final velocity, which is 16.2. We've got our distance, which is s, which is 240, and we're trying to find the deacceleration, which is going to be our a value, so we can discount the t. Now looking at this, which formula uses s, u, v and t, so yes, u, v and a, and that's going to be this formula here. So for this we're using v squared equals u squared plus 2as. Substituting these numbers in, we get 16.2 squared equals 26.3 squared plus 2 lots of 240a. They're doing a bit of rearranging now. I know some of you may be tempted to wanting to square what 16.2 is and what 26.3 squared is, but the problem with that is you're going to be working with some potentially quite long decimal numbers. So what I would always recommend students to do is just to keep it in this form at this moment in time. So for this we've got 16.2 squared minus 26.3 squared equals, and that's going to be 480a. And then we get 16.2 squared minus 26.3 squared divided by 480, and that equals a. And typing that into my calculator, I get an a value of negative 0.894, and the units are going to be meters per second squared. Now it's worth noting that in the question actually asks for us to find the deacceleration, so therefore the deacceleration is going to be 0.894 meters per second squared. So it's really important that you read the question carefully and also read what the actual answer is, what they're actually asking for. So if the question asks for acceleration, then an answer of minus 0.894 would be correct, but because it's asking for deacceleration, we need to therefore give a positive number, because what you don't want to do is two negatives cancelling each other out. So always be mindful of that. And likewise, if you're given a question where it's deaccelerating, then your A value is going to be negative. So just make sure you're reading the questions carefully and not losing any silly marks on signs. So moving on to our fifth example, it says a particle reduces its speed from 16.3 meters per second to 7.5 meters per second while travelling 120 meters. For part A, it's asking us to find the constant acceleration of the particle. So this question very similar to our previous one. So first of all, like always, let's start by writing our SUVAT to help us establish which formula we're going to be using. So here from this we know that displacement is 120, u is our initial velocity, which is 16.3, our final velocity is 7.5, and what we're trying to find is the acceleration. Now again, it's always worth making sure that the units are correct and the same distance units is used and the same time units is used before we continue. Now once we're happy with that, we're then looking for a formula that uses S, U, V and A, and that is going to be our third one here. So typing all this in and substituting the values in, and again, always good practice to write down the formulas. If anything, just to save us when we're checking our work to make sure we've not made any silly mistakes. So here we've got 7.5 squared equals 16.3 squared plus 2 times 120 times A. Now working out what A is, it's going to be 7.5 squared minus 16.3 squared, all divided by 2 times 120, and that gives me an A value of minus 0.893. Now unlike the previous example where it's asked for deacceleration, this one just says the constant acceleration, so a negative value is absolutely acceptable. Now for the second part of the question, it's asking us to find the distance of the particle would travel in another 5 seconds. Now for this particular question, as you can see, it's two parts, so it's using what we had in our first part. So if this is part A, this is going to be our part B, and it says find the distance the particle would travel for another 5 seconds. So B lasts for a total of 5 seconds. The initial velocity will be the final velocity in part A, so that's going to be at 7.5 meters per second. And what then going to use is start by writing our SUVAT, in which my initial velocity is 7.5. My acceleration is going to be what it was in part A, which was minus 0.893. The time is in 5 seconds. And what the question is asking me is to find the distance. So I'm not going to be using V. So which formula uses S, U, A and T? Well, it's going to be this one here. And so using that formula, if I write that down, SU equals UT plus a half AT squared. Substituting those numbers in, I get S equals 7.5 multiplied by 5 plus 0.5 multiplied by A, which is minus 0.893. Multiplied by T squared, which is 5 squared. So plugging that all into my calculator, I get an S value of 26.6, and that's to 3 significant figures. Now it's worth just checking that all my distance units are in meters, so that's going to be in meters as well. So example 6 says a train leaves the station from rest with a constant acceleration of 0.2 meters per second squared. It reaches its maximum speed after 2 minutes and maintains this speed for a further 4 minutes when it slows down to a stop at a second station with an acceleration of minus 1.5 meters per second squared. And the question is asking us to find out how far apart are the two stations. Now, hopefully before you get started working these scripts, by reading the question, hopefully you notice that this one just reads differently. And there is a reason behind that, and the reason for that is that we've got 3 different rates of acceleration. Now, one way to describe a particular question is to draw a diagram. So if we start by drawing a velocity time graph, then what we know is that the train leaves the first station at a constant acceleration. And then we've got the train has a constant velocity, and then as it approaches the second station, it deaccelerates at a constant rate. So what we have is we've got a graph of 3 different sections, which is A, B, and C. Now, another alternative is you can do is just draw a straight line and just kind of mark the different sections that we've got. So here we've got A, we've got B, and we've got C. Now, just be mindful of the letters that you use. Make sure you're not getting confused with the letters that are in the SUVAT formulas. So if we look at this very first one, what we're ultimately trying to find is S. So what we need to do is find the total displacement. So for each of those 3 sections, what we need to do is we need to find S in every single one of these. So looking at the first section, and if I start by writing SUVAT, then what we know from that first section is that we are trying to find S. The initial velocity is going to be 0. The final velocity we don't know. We know that the acceleration is 0.2 meters per second squared, and the time is 2 minutes. Now, what you need to do is just be mindful of the units being used. As you can see, acceleration is given as meters per second squared, so all our time units need to be in seconds and all our distance units need to be in meters. So 2 minutes is represented by 120 seconds. Now, from this we can then work out what S is, and the formula we're going to use for that is going to be S equals UT plus a half AT squared. So substituting the values in, we've got S equals, and then UT is just going to be 0 plus a half A, which is 0.2, multiplied by T, which is 120 squared. Now if I type that all into my calculator, I should end up with an S value of 1,440 meters. So that's my first S done. So now let's have a look at the second section. So this is our B section. So looking at B, let's start this as we always do by writing SUVAT. Now S is what I'm trying to find out, which I'm just going to call X. U is, I don't know that. V, I'm not sure what that is. A, you can see we've got a constant velocity, so acceleration is going to be 0, and the time, which is 4 minutes, which we again need to make sure we're working in seconds, is going to be 240. Now with this, as we're supposed to know 3 of the items to find the 4th, we need to recognize that the initial velocity and the final velocity are going to be the same, but in order to find the initial velocity, that's going to be the final velocity of the last section. So first thing we need to do is we actually need to use this information here, in which I can now write what S is, which is 1,440, to then work out what V is going to be. So from this, I can then work out V. So if I pick one of the formulas, let's go for V equals U plus AT. And V is going to equal U, which is 0, plus AT, which is 2 times 120. So V is going to equal, that should be 0.2 rather, in which we get a V value of 24. So from this, what I can then do is go back to my SUVAT for B, and I can write U as 24 and V as 24 as well. Now from this, I can then work out what S is, so I pick a formula in which I've got the 4, so I can pretty much use any formula that uses S. So let's go for S equals a half U plus V multiplied by T, in which then substituting numbers in, I get S equals a half 24 plus 24 multiplied by 240, and that's coming off the screen, so let's just make sure that fits in which, typing that all into my calculator, I get an S value of 5,760. Now the screen's looking a bit messy, so let's just get rid of some of the information that I've got. So now let's focus on our last section, which is this point here. So from this, what we then know, we start by writing our SUVAT, in which S is what we're looking for, so let's just call that X. I've got our initial velocity, which is our final velocity of section B, which was 24. We've got our final velocity, which is going to be 0, our acceleration rate or deceleration rate, which is minus 1.5. And just again, make sure that if it mentions deacceleration, that acceleration is going to be negative, but as this, it tells me in the question that acceleration is always a negative number, so we don't need to worry about that. And for the final one, we don't know what the time takes in that section, so we leave that one blank. So what we're looking for is which formula uses S, U, V and A, and that's going to be our third one. So then using V squared equals U squared plus 2AS, substituting those numbers in, we get 0 equals 24 squared plus 2 times A, which is minus 1.5, and we've got S. And then simplifying all of that, what we end up with is an S value of 192. So all that's left for me to then do is answer the question, which is how far away are the two stations? So the total distance or displacement, whichever you want to call this, is going to be 1440 plus 5760 plus 192, which gives me a grand total of 7,392. Let me just write that a little bit neater. 92, and again, don't forget the units, and there we go.